for respectively P2R and R2 by 2. So then, here's the deal. What I do is I take my point in P, so here's my P2, P2R, all right. T maps you over here like so to this guy, which is R2 by 2, all right? Okay. Now, I take an arbitrary thing of the domain. What's an arbitrary thing of the domain look like? It's something like A plus bx plus cx squared. Let me call this thing v, just to give it a name, v. So then that, you see, I can trade for what? Down here I've got the coordinate map, phi beta, right? Coordinate map phi beta says that, hey, v beta, the coordinate vector, all right, the coordinate vector of this vector is just ABC in my current basis choice, right? ABC. All right. And then, where does t go to? Well, that depends on the details of the whatever nonsense I just made up for you. In this case, I made this up, right? So if I feed this f of x, right? You can see this is f of x, right? Into here, what do you get? Well, put it over here. We get t of f of x, which you could say is t of v. I'll want t of f of x. Fine. F of 0 is what? F of 0 is a. F prime of 0 is what? Differentiate this, you get b. F prime prime of 0 gives you 2c. And then you've got 0. Okay, so that right there, folks, is the image of an arbitrary vector in the domain under the given linear transformation. My next order of business is to find the coordinate vector of this with respect to my choice of basis for the codomain, which is gamma. Now, that's simple. Piece of business, because over here we have R4. All right? Now, R4 is, what is it? It's, what's the coordinate vector here? I listed them in this order, right? So that's actually, you could write this out. I don't really need to do this, but I'll do it just for a second. This is really A, E11, plus B, E12, plus 2C, E21, plus 0, E22, okay? The coefficients then are the coordinates. Coordinate. That's why I put down here the coordinate of TV with respect to the gamma basis is this 4 vector. It's A, B, 2C, and 0. All right, now you see we're almost there. If I want to realize this abstract linear transformation as a matrix multiplication, I can do so at the level of coordinates. You see, to get from here to here, I can multiply by what's called the matrix of T with respect to the basis beta gamma. See, now we can't just use square brackets, because we could use square brackets before because we were working with column vectors to column vectors. There's a standard basis choice. There was no ambiguity. Now there's tons of ambiguity in how you choose coordinates. So the matrix of the linear transformation has to have a notation which reflects that ambiguity. In this case, the choice of basis in the range and the codomain gamma and in the domain beta. And okay, so the question is, what is that matrix? Well, then you can just kind of I usually fill in the blanks. Easiest thing for me to do. I'm going from R3 to R4. That means I want a 4 by 3 matrix. 4 rows, 3 columns. And I want something that when I multiply by ABC, out pops A, B, 2C, and 0. All right? And then what I do is I write that, and then I just fill in the blanks, just looking at the formula that I already have. Right? Like, okay, so I look over here, I'm like, okay, so A, I have to produce an A in the output, right? So that makes me put 1, 0, 0 here. To get that B, I have to put 0, 1, 0. To get that C, I need 0, 0, 2. And to get that 0, I just put zeros. And there you have it. That is the matrix of T with respect to the basis beta gamma. That's how you calculate, or at least one way to calculate the matrix of an abstract linear transformation. Now, there are other ways to do it. I don't always do it this way. Sometimes it's slicker to do it another way. Now, I guess I should tell you that this, right, is actually the mapping L sub, oh man, I didn't talk about this today. That's for shame. This is L sub T beta gamma. In other words, it's the linear transformation which is induced by multiplying by that matrix. And as a functional equation, I can write this. I can say L sub T beta gamma is equal to what? In other words, this arrow right here is the same as doing this. Let me make it a trip. I'll take the trip in my silly pink marker. Here it is. Sorry, that's how I feel. Let's see here. Like that. So this trip would be last comes first. So phi gamma. That's the last thing to hit the argument. Composed with t. And then the first thing was phi beta inverse. So in fact, you could define the standard, the basis t beta, the matrix t beta gamma. You could say, in fact, it's the standard matrix of this mapping, phi gamma composed with t composed with phi beta inverse. That would make sense because what I'm just writing and putting in a box is this guy right here is a linear transformation from in this case R3 to R4. And there's nothing really special about this example, this idea about drawing this picture. It just works as well for like if this was a two-dimensional and that was five-dimensional or whatever. Totally generalizes. So this is always a bit much the first time you see it, but I'll do this a few more times. And once you see what's going on, it's really pretty nice. And almost all of my students understand this by the time they're done studying, and usually get it on the test just fine. It's unfortunate it's not in more books, by the way. But anyway, I digress. We'll talk more about this. In particular, we're going to be interested in the question, and this is a harder question, is like if you chose different bases, right? If I chose beta bar and gamma bar, different choices of basis for this guy and that guy, then how would that reflect in the matrix, say T, with respect to the beta bar gamma bar matrix? But that's not something I can discuss too fast. And this is a pretty good stopping point. I hope this is enough for you to at least take a stab at some of the homework. And of course, you're free to ask me questions, email. Maybe I can post another video if there's some good questions. So anyway, thanks guys for your patience. Sorry about this video. Bye-bye.